In this video, we will learn strength of acid and bases in organic molecules. In the first chapter of IIT JAM syllabus of organic chemistry, there is a topic about strength of acid and base. So before we solve questions on strength of acid and base, we must know some basic theory of acid and bases. So the first theory is Bronsted theory. So the theory says an acid is defined as a proton donor and a base as a proton acceptor. Here the proton means H plus ion. So a base must have a pair of electrons available to share with protons, that is H plus ion. So now this pair of electron may present as an unshared pair, that is lone pair of electrons or negative charge in the base with which the proton will coordinate. So, atoms or molecules having lone pair of electrons participate in acid-base reaction as a base. For example, all amines and alkoxides are base. Again, all carboxylic acids that have H plus ion or proton act as acids in Bronsted theory. So next come your conjugate acid-base theory. An acid-base reaction is simply the transfer of proton from an acid to a base. Here let us consider an acid AH. Transfer its proton to base and converts to A-. Now the A- has capability to accept proton. That is why it is termed as conjugate base, and it is the conjugate base of acid AJ. Again, the base B- in the left hand side, which have unshared pair of electron or negative charge, accept the proton, that is H plus ion, from acid HA and become BH plus. That means it has now capability of donating H plus ion. So this is termed as conjugate acid, and this is the conjugate acid of the base B-. Now, always remember, a strong acid will be the one which can easily donate its proton and whose conjugate base will be the weaker one, which means conjugate base has least tendency to accept proton. Here, the conjugate base of acid HA will be stronger only when the acid HA will be weaker. But if the acid HA is strong, then its conjugate base will have to be weak. Now, Lewis acids and bases theory. Here, Lewis defined acids as molecules or ions capable of coordinating with unshared electron pairs, and bases as molecular ions which have such unshared electron pairs available for coordination. Here, the unshared electron pair of the base forms a covalent bond with the vacant orbital of the acid. In general, the Lewis acid-base reaction is as follows. For example, AlCl3, BF3, ZnCl2 are Lewis acids, where amines are Lewis bases. In amines, the nitrogen atom has unshared electron pair or lone pair of electron that combine or coordinate with Lewis acid BF3, forming a charged species. Now, the facility with which an acid-base reaction takes place depends not only on the strength of acid and base but also on hardness or softness of the acid and base. Now, according to Lewis acid-base theory, acid accepts electron pair from base. That means an acid can be hard only when if it has high positive charge and it do not contain any unshared electron pairs in their valence shell, and it is of high electronegativity, that it attracts bonding electron pairs towards itself more strongly. Low polarizability means as it has high positive charge and it is small in shape, that is why it cannot be polarized in presence of base. That means it will hold the electron pair or the bonding electron pair strongly. So here are some example of hard acids where we can see that each ions have high positive charge and they are comparatively small in shape. Again, the soft acid is the large acceptor atoms with low positive charge and it have unshared electron pair and it is highly polarizable and low electronegativity. That means it holds the bonding electron pair less strongly compared to hard acid. That is why it is soft acid. Some example of soft acids are Cu plus, Ag plus, Pd2 plus, Pt2 plus, Ag2 plus. Here you can see in copper plus that it has unshared pair of electrons in its outermost d orbital. That is why it has relatively less tendency to accept electron. That is why it is called soft acid. Then hard bases are those which are highly electronegative donor atoms of low polarizability. It holds its valence electron tightly. Here you can see some example of hard bases are H2O, OH minus, fluorine minus, SCO minus, SO4 minus. They all are in ionic forms having more electrons than its original form. That is why it donates its electron easily, and remember they are of high electronegativity. That means they do not easily donate electrons. On the other hand, soft bases have low electronegativity, high polarizability, and hold valence electrons loosely. That means it easily donate electrons. Here are some examples of soft bases. Now, SHAB principle or hard soft acid base principle says hard acids prefer to bond to hard bases and soft acids prefer to bond to soft bases. This rule has nothing to do with acid or base strength, but it says that the product of acid-base reaction will have extra stability if both acid and base are hard or if both are soft. Generally, soft Lewis acid and soft Lewis base tend to form a covalent bond. This is because covalent bond formation occurred by sharing of electron pair between the bonded atoms. So, as both soft acid and soft bases are of high electronegativity and low polarizability, that is why they tend to form covalent bond and become stable, while a hard acid and hard base tend to bond ionically. Now, how to measure the strength of acid and bases in organic molecule? Here, pK play the role. The extent at which an acid can lose proton in solvent medium which act as a base is called the strength of that acid or acidity of that acid. Here you can say an acid Ha in solvent H2, that is water, dissociates completely, forming H3O plus, that is hydronium cation, and A minus anion. So now we can write the Ka, that is the dissociation constant or ionization constant of the acid H. So the rule of writing Ka or the constant is putting the value of or the concentration of the product molecule in the numerator position as the numerator and the reactant molecules as a denominator. Here the H3O plus in third bracket says concentration of H3O plus, and if we slide the concentration of H2O to the left hand side, because concentration of H2O is constant in the reaction, find another value Ka prime. Here the Ka or Ka prime both is called the dissociation constant or ionization constant, and it is the measure of the acidity of the acid. Ka is also called acidity constant of the acid in water. Because of exceedingly small numerical value of Ka, it is generally expressed as minus log base 10 Ka. So the value of pKa, where pKa is equal to minus log 10 Ka. So now the Ka and pKa values can be used to compare the acidities of organic acids. Thus, we can conclude that greater the value of Ka, that is lower the value of pKa, as pKa is equal to minus log 10 Ka. Greater will be the ionization and higher will be acidity. Similarly, lower the value of Ka, that is higher will be the value of pKa, and lower will be the dissociation and lower will be the acidity. So that's how we measure the strength of acid. Now measure the strength of base. So again, in that case, we take base B in solvent H2O, where it gets dissociated completely, forming BH plus cation and OH minus ion. Here, BH plus is the conjugate acid of base B and OH minus is the conjugate base of solvent H2O. Now we can conclude or write Kb, or the dissociation constant or the basicity constant, as product molecule at the numerator position and the reactant molecule or the concentration of reactant molecule at the denominator position. And again, sliding concentration of H2 at the left hand side with Kb, we get another constant Kb prime. Here both Kb and Kb prime is said dissociation constant as the concentration of H2 is constant. So we can conclude again that pKb is equal to, but pKb can be written as minus log 10 Kb. So again we can conclude that the greater the value of Kb or lower the value of pKb, greater will be its basicity. Again, lower the value of Kb or greater the value of pKb, lower will be its basicity. Now, basicity can also be measured by pKa values. Let us consider an acid or conjugate acid of base B, BH plus, and the solvent H2O, and after the reaction they become base B plus H3O plus in the right hand side. So again we write the value of Ka and find that concentration of B and H3O plus at the numerator position and BH plus at the denominator position. So now if we increase the concentration of B or base in the equation, we will get greater Ka value. That means if the concentration of base rise, it means concentration of conjugate acid in the left hand side BH plus decreases steadily. BH plus will be highly acidic in nature. Greater Ka value means stronger acid, and if we decrease concentration of B, BH plus do not dissociate completely or share its proton to the solvent readily. That means it is less acidic in nature. Thus we get lower Ka value. So again here came the value of pK, that is minus log 10 Ka. So if we get greater Ka value, we will have lesser pK value, that means higher acidic nature. Now the question is why pKb value of trimethylamine is greater than pKb value of dimethylamine. This is because of the influence of solvent on acidity and basicity. So acids on ionization generates its conjugate base. These anionic species strongly polarize nearby solvent molecules. The solvent molecule then form an envelope around the anion and thus solvate it. The greater the extent of this envelope formation, the greater will be its solvation. Here, dimethylamine cation, being smaller in size than trimethylamine, undergo more solvation than that of trimethylamine. And the greater the solvation of a species in a solvent, lower will be its energy and greater will be its stability. That is why dimethylamine cation get extra stability in solvent, but trimethylamine cation having undergo less solvation in solvent get less stability. That is why in water medium trimethylamine is less basic than dimethylamine. That means trimethylamine has lower Ka value than dimethylamine, and again trimethylamine has greater pKb value than dimethylamine. Again we know that pKa value is opposite of pKb value. That means if pKa value increases, pKb value decreases and vice versa. That is why pKa value of trimethylamine is lower than pKa value of dimethylamine. Now, the last question is, picric acid is stronger than HBr in DMF, but in water HBr is stronger acid. This is due to the difference in sizes of the conjugate bases. The larger conjugate base, trinitrophenoxide ion, that is picric acid, is more solvated in DMF than smaller Br minus, which is again more solvated in water. And in polar protic solvent like water, the solvation is occurred by forming hydrogen bond. So if the acid is large, then its conjugate base will be large, and that is why its solvation will decrease. Thus it get less stability, and the conjugate base get the greater tendency to take protons, the greater value of Ka and the less value of pKa. But in polar aprotic solvent like DMF, the solvation increases with the size of anion in solvent. I hope guys you understand what I want to say in this video. So if you like this video, please don't forget to comment and do subscribe to get regular update from this channel. Thank you for watching. I hope guys you understand what I want